Somewhere in the depths of space, amidst the swirling cosmic dance of stars, lies a phenomenon so awe-inspiring it challenges the very fabric of our understanding: supermassive star explosions. Imagine stars 10 billion times larger than our Sun, their colossal forms teetering on the edge of oblivion, ready to unleash a cataclysmic display of energy that reverberates across the cosmos. Join us as we embark on a journey beyond the bounds of imagination, where the universe itself becomes the stage for a spectacle of cosmic proportions. Brace yourself for an exploration of supermassive star explosions that will ignite your curiosity and expand your vision of the cosmos. Stars, the celestial beacons that have captured humanity's imagination for millennia, are not merely twinkling lights in the night sky, but colossal entities of immense power and significance in the cosmos. To understand the phenomenon of stars is to embark on a journey through the vast expanse of space and time, exploring the intricate processes that govern their formation, evolution, and ultimate fate. At the heart of every star's existence lies the relentless force of gravity, drawing together vast clouds of gas and dust scattered throughout the cosmos. These clouds, known as molecular clouds, are colossal reservoirs of raw materials, primarily hydrogen and helium, left over from the birth of the universe in the aftermath of the Big Bang. Over millions of years, gravitational attraction causes these clouds to condense and collapse, giving rise to the birth of stars. As the gravitational collapse intensifies, the core of the protostar grows increasingly dense and hot, triggering nuclear fusion, the process by which hydrogen atoms are fused together to form helium, releasing a tremendous amount of energy in the process. This fusion reaction is the fundamental engine that powers a star, generating the heat and light that illuminate the cosmos. Once nuclear fusion ignites in the core, a star enters its main sequence phase, characterized by a delicate balance between the inward pull of gravity and the outward pressure generated by the fusion reactions. This equilibrium sustains the star for millions or even billions of years, during which it shines steadily, casting its radiant glow across the void of space. However, the life of a star is not eternal, and its fate is determined by its mass. Low-mass stars, such as red dwarfs, burn through their hydrogen fuel reserves slowly, gradually swelling into red giants before shedding their outer layers to form planetary nebulae and eventually fading into white dwarfs, a dense stellar remnant the size of a planet. In contrast, high-mass stars lead more tumultuous lives, burning through their fuel at a rapid pace and undergoing a series of dramatic transformations. When a high-mass star exhausts its hydrogen fuel, it embarks on a cataclysmic journey toward its ultimate demise. The core contracts under its own gravity, heating up until it is hot enough to ignite helium fusion, triggering a new phase of nuclear reactions. These successive stages of fusion produce increasingly heavier elements, from carbon and oxygen to silicon and iron, as the star marches inexorably toward its fate. Yet when the star's core becomes iron-rich, a critical threshold is crossed, and the balance between gravity and radiation pressure collapses catastrophically. The core implodes in a fraction of a second, while the outer layers are ejected into space in a brilliant explosion known as a supernova. During this violent event, a supernova can outshine entire galaxies, briefly illuminating the cosmos with its brilliance before fading into obscurity. In its wake, the remnants of the star may form a neutron star, a dense city-sized object composed almost entirely of neutrons, or in the case of the most massive stars, collapse into a black hole, an enigmatic singularity where gravity's grip is so intense that not even light can escape. The phenomenon of stars encompasses a vast array of cosmic processes, from the serene glow of newborn stars to the explosive demise of supernovae and the enigmatic mysteries of black holes. Through their radiant light and titanic forces, stars shape the fabric of the universe, illuminating the darkness of space and inspiring wonder in the hearts and minds of all who gaze upon them. In the vast tapestry of the cosmos, where stars dot the celestial canvas, there exists a class of stellar behemoths that defy imagination. Stars so colossal, so immense, that they dwarf our own sun in comparison. These cosmic giants, larger than life itself, challenge our understanding of the universe and beckon us to explore the frontiers of astronomical knowledge. The concept of stars larger than the sun is not merely an abstraction but a profound revelation of the staggering diversity and complexity of the cosmos. While our sun serves as a familiar beacon in the sky, a source of warmth and light that sustains life on Earth, there exist stars whose dimensions exceed even the wildest imaginations of science fiction. At the heart of this concept lies a fundamental truth. The size of a star is intricately linked to its mass, with gravity playing a pivotal role in shaping its destiny. Stars that are larger than the Sun possess a greater mass, resulting in more intense gravitational forces that compress their cores to extraordinary densities and temperatures. The sheer scale of these stellar giants is awe-inspiring. Whereas the Sun boasts a diameter of approximately 1.4 million kilometers, enough to engulf more than 1 million Earths, stars larger than the Sun dwarf even this colossal size. They can span hundreds or even thousands of times the diameter of our own Sun, stretching across the vastness of space like titanic beacons of light. Yet the magnificence of these stellar giants is not merely a matter of size, but of profound implications for the cosmos at large. Stars larger than the Sun play a pivotal role in shaping the dynamics of their galactic environments, influencing the formation of planetary systems, the evolution of galaxies, and even the synthesis of heavy elements essential for life. Moreover, the life cycle of these massive stars is a dramatic saga of cosmic proportions, marked by spectacular events such as supernova explosions and the formation of exotic stellar remnants like neutron stars and black holes. In their fiery crucibles, elements essential for life such as carbon, oxygen, and iron are forged, seeding the cosmos with the building blocks of future worlds. The exploration of stars larger than the Sun is not merely an academic pursuit, but a journey of discovery that unlocks the secrets of the universe itself. By studying these cosmic behemoths, astronomers gain invaluable insights into the processes that govern the birth, life, and death of stars, shedding light on the fundamental forces that shape the cosmos. As we peer into the depths of space, marveling at the splendor of these celestial giants, we are reminded of the boundless wonders that await us in the cosmos. Stars larger than the Sun stand as monuments to the grandeur of the universe, beckoning humanity to venture ever further into the unknown, driven by an insatiable thirst for knowledge and a profound sense of wonder. In the vast cosmic theater where stars are the celestial actors, some performances stand out as truly spectacular. Imagine a star so colossal, so immense that it defies comprehension, a titanic behemoth whose brilliance outshines entire galaxies. Now picture this stellar giant reaching the climax of its cosmic saga, hurtling towards an explosive finale of cosmic proportions. This is the preview of our topic: stars 10 billion times bigger than the Sun set to explode. In this cosmic drama, we are thrust into a world where scale knows no bounds, where stars are measured not in millions or billions, but in magnitudes unimaginable. These supermassive stars, 10 billion times larger than our own Sun, are the cosmic heavyweights of the universe, dominating the celestial stage with their sheer size and power. But despite their majestic presence, these stellar behemoths are not eternal. Like all stars, they are bound by the inexorable forces of nature, hurtling towards their ultimate fate with the relentless march of time. And as they approach the twilight of their existence, they set the stage for a cosmic spectacle unlike anything witnessed before. The impending explosion of these supermassive stars is not merely a footnote in the annals of astronomical history, but a cataclysmic event of cosmic proportions. When these titanic giants exhaust their nuclear fuel, they undergo a violent transformation, culminating in a breathtaking display of stellar fireworks known as a supernova. In this explosive finale, the star's core collapses under its own gravity, triggering a chain reaction of nuclear fusion that releases an unfathomable amount of energy in a fraction of a second. The resulting explosion sends shockwaves rippling through space, scattering the star's outer layers across the cosmos and illuminating the heavens with its brilliant light. But the drama doesn't end there. In the aftermath of the supernova, the remnants of the star may give rise to some of the most enigmatic objects in the universe, from neutron stars, dense stellar corpses packed with more mass than the Sun, to black holes, cosmic singularities where gravity's grip is so intense that not even light can escape. As we peer into the depths of space, witnessing the grand finale of these supermassive stars, we are reminded of the profound forces that shape the cosmos. From the fiery birth of stars to their explosive deaths, The universe is a stage where cosmic dramas unfold on a scale beyond comprehension, inviting us to ponder the mysteries of existence and our place within it. Join us on this journey into the heart of the cosmos, where stars 10 billion times bigger than the Sun are set to explode, illuminating the darkness of space with their brilliant light and inspiring wonder in the hearts and minds of all who gaze upon them. In the vast expanse of the cosmos, stars are not static entities, but dynamic beings undergoing a continuous process of transformation, a cosmic ballet of birth, life, and death known as stellar evolution. To understand this intricate dance is to peer into the very heart of the universe, where the forces of nature sculpt the fabric of reality itself. At the dawn of time, in the cold depths of interstellar space, molecular clouds, vast reservoirs of gas and dust, lurk like cosmic incubators, nurturing the seeds of future stars. Within these dense clouds, gravity reigns supreme, drawing together particles of gas and dust to form protostellar cores, the embryonic precursors of stars. As these cores collapse under the relentless pull of gravity, they grow hotter and denser, eventually reaching temperatures and pressures sufficient to ignite nuclear fusion, the fundamental process that powers all stars. Thus, a new star is born, casting its radiant light into the darkness of space and marking the beginning of its journey through the cosmos. In its infancy, a star resides on the main sequence, a stable phase of stellar evolution characterized by a delicate balance between the inward force of gravity and the outward pressure generated by nuclear fusion. During this stage, the star shines steadily, converting hydrogen into helium in its core and radiating energy into space in the form of light and heat. But like all things in the universe, stars are subject to change, and as their nuclear fuel is consumed, they undergo a series of transformations that shape their destiny. For low-mass stars like our Sun, this journey is a gradual one, marked by the swelling of the star into a red giant as it exhausts its hydrogen fuel reserves. In its twilight years, a red giant sheds its outer layers in a stunning display of cosmic beauty, forming a planetary nebula, a luminous shell of gas and dust that envelops the aging star's core. Left behind is a stellar remnant known as a white dwarf, a dense, Earth-sized object composed primarily of carbon and oxygen, slowly cooling over billions of years. But for high-mass stars, the story is far more dramatic. Fueled by the intense heat of nuclear fusion, these stellar behemoths burn through their fuel at a rapid pace, hurtling towards their ultimate demise with breathtaking speed. When a high-mass star exhausts its nuclear fuel, it undergoes a cataclysmic collapse, triggering a supernova, an explosive event that outshines entire galaxies and scatters heavy elements across the cosmos. In the aftermath of a supernova, the remnants of the star may give rise to some of the most exotic objects in the universe, from neutron stars, dense stellar corpses pulsating with intense energy, to black holes, enigmatic singularities where the laws of physics break down and the very fabric of space-time is warped beyond recognition. Through the lens of stellar evolution, we gain profound insights into the workings of the cosmos, from the birth of stars in the depths of interstellar clouds to their explosive deaths in cataclysmic supernova explosions. It is a journey that spans billions of years and traverses the vast expanse of space, revealing the interconnectedness of all things in the grand tapestry of the universe. In the grand tapestry of the cosmos, stars are the cosmic architects of the universe, shaping the fabric of space and time through their radiant light and titanic forces. Their life cycle, a majestic saga of birth, evolution, and death, unfolds over billions of years, leaving an indelible mark on the cosmos and illuminating the mysteries of existence itself. The life cycle of a star begins in the cold depths of interstellar space, where vast clouds of gas and dust, known as molecular clouds, lurk like cosmic incubators, nurturing the seeds of future stars. Within these dense clouds, gravity exerts its inexorable pull, drawing together particles of gas and dust to form protostellar cores, the embryonic precursors of stars. As these cores collapse under the relentless force of gravity, they grow hotter and denser, eventually reaching temperatures and pressures sufficient to ignite nuclear fusion, the fundamental process that powers all stars. Thus, a new star is born, casting its radiant light into the darkness of space and marking the beginning of its journey through the cosmos. In its infancy, a star resides on the main sequence, a stable phase of stellar evolution characterized by a delicate balance between the inward force of gravity and the outward pressure generated by nuclear fusion. During this stage, the star shines steadily, converting hydrogen into helium in its core and radiating energy into space in the form of light and heat. But like all things in the universe, stars are subject to change, and as their nuclear fuel is consumed, they undergo a series of transformations that shape their destiny. For low-mass stars like our Sun, this journey is a gradual one, marked by the swelling of the star into a red giant as it exhausts its hydrogen fuel reserves. In its twilight years, a red giant sheds its outer layers in a stunning display of cosmic beauty, forming a planetary nebula, a luminous shell of gas and dust that envelops the aging star's core. Left behind is a stellar remnant known as a white dwarf, a dense, Earth-sized object composed primarily of carbon and oxygen, slowly cooling over billions of years. But for high-mass stars, the story is far more dramatic. Fueled by the intense heat of nuclear fusion, these stellar behemoths burn through their fuel at a rapid pace, hurtling towards their ultimate demise with breathtaking speed. When a high-mass star exhausts its nuclear fuel, it undergoes a cataclysmic collapse, triggering a supernova, an explosive event that outshines entire galaxies and scatters heavy elements across the cosmos. In the aftermath of a supernova, the remnants of the star may give rise to some of the most exotic objects in the universe, from neutron stars, dense stellar corpses pulsating with intense energy, to black holes, enigmatic singularities where the laws of physics break down and the very fabric of space-time is warped beyond recognition. Through the lens of stellar evolution, we gain profound insights into the workings of the cosmos, from the birth of stars in the depths of interstellar clouds to their explosive deaths in cataclysmic supernova explosions. It is a journey that spans billions of years and traverses the vast expanse of space, revealing the interconnectedness of all things in the grand tapestry of the universe. Stars, the cosmic engines that fuel the universe, undergo a remarkable journey of evolution dictated by their mass, a fundamental property that shapes their destiny and governs the cosmic processes that unfold throughout their existence. From the humble beginnings of protostellar cores to the cataclysmic finales of supernova explosions, the evolution of stars is a testament to the intricate interplay of gravity, nuclear fusion, and stellar dynamics. Stars with masses similar to or lower than that of our Sun, known as low-mass stars, follow a relatively gentle evolutionary path characterized by slow, steady transformations over billions of years. At the onset of their lives, these stars form from the gravitational collapse of molecular clouds, giving rise to protostellar cores that gradually accumulate mass until nuclear fusion ignites in their cores. During their main sequence phase, low-mass stars shine steadily, fusing hydrogen into helium in their cores and radiating energy into space as light and heat. This phase can last for billions of years, during which the star remains stable and luminous, providing a nurturing environment for any orbiting planets. As the star ages and exhausts its hydrogen fuel reserves, its core contracts and heats up, causing the outer layers to expand and the star to swell into a red giant. During this phase, the star's outer layers become unstable, leading to the shedding of its outer envelope in the form of a planetary nebula. Left behind is a white dwarf, a dense, Earth-sized remnant composed primarily of carbon and oxygen that gradually cools over billions of years, fading into cosmic obscurity as it enters its final stages of stellar evolution. In contrast to their low-mass counterparts, high-mass stars, those with masses several times greater than that of the Sun, lead far more tumultuous and dramatic lives, marked by rapid transformations and violent cataclysms. At the outset, high-mass stars form from the gravitational collapse of massive molecular clouds, rapidly accreting mass until the core becomes hot and dense enough to initiate nuclear fusion. The intense heat and pressure generated by nuclear fusion cause these stars to burn through their hydrogen fuel at a staggering pace, leading to a relatively short main sequence phase compared to low-mass stars. As high-mass stars near the end of their main sequence phase, they undergo a series of nuclear reactions that give rise to increasingly heavier elements, from helium and carbon to oxygen and iron. When the core becomes iron-rich, a critical threshold is crossed, triggering a catastrophic collapse known as a core collapse supernova. During this explosive event, the star's core implodes under its own gravity, releasing an immense amount of energy in a fraction of a second. The resulting shockwave tears through the star's outer layers, scattering heavy elements across the cosmos and illuminating the heavens with its brilliant light. In the aftermath of a supernova, the remnants of the star may give rise to some of the most exotic objects in the universe, from neutron stars, dense stellar corpses pulsating with intense energy, to black holes, enigmatic singularities where gravity's grip is so intense that not even light can escape. Through the lens of stellar evolution, we gain profound insights into the workings of the cosmos, from the birth of stars in the depths of interstellar clouds to their explosive deaths in cataclysmic supernova explosions. It is a journey that spans billions of years and traverses the vast expanse of space, revealing the interconnectedness of all things in the grand tapestry of the universe. In the vast expanse of the cosmos, where stars dot the celestial canvas with their radiant light, there exist titanic behemoths, massive stars whose brilliance outshines entire galaxies. These celestial giants, born from the tumultuous depths of interstellar clouds, defy conventional notions of scale and power, casting their radiant glow across the cosmos and shaping the destiny of the universe itself. The introduction to massive stars is an exploration into the realm of cosmic extremes, where the forces of gravity and nuclear fusion conspire to create some of the most awe-inspiring phenomena in the cosmos. Unlike their more modest counterparts, massive stars possess an extraordinary mass, measured in multiples of the Sun's own considerable weight. At the heart of these stellar giants lies a cosmic crucible of unimaginable heat and pressure, where nuclear fusion reigns supreme and elements are forged in the fiery depths of their cores. Unlike low-mass stars, which burn through their nuclear fuel at a leisurely pace, massive stars are cosmic powerhouses, consuming their hydrogen fuel reserves with breathtaking speed and intensity. The sheer scale of these celestial titans is staggering. While our own Sun is a formidable entity in its own right, boasting a mass roughly 330,000 times that of Earth, massive stars dwarf even this colossal size. Some can weigh in at tens or even hundreds of times the mass of the Sun, stretching the limits of our understanding and challenging the boundaries of the known universe. But it is not merely their size that sets massive stars apart. It is their unique characteristics and remarkable behavior that captivate the imagination of astronomers and stargazers alike. From their luminous brilliance to their violent deaths in cataclysmic supernova explosions, massive stars are cosmic phenomena of unparalleled significance and complexity. Throughout their lives, massive stars exhibit a dynamic interplay of forces, from the relentless pull of gravity that compresses their cores to the fiery inferno of nuclear fusion that sustains their brilliance. They shine with a luminosity far surpassing that of their low-mass counterparts, illuminating the heavens with their radiant light and shaping the environments in which they reside. Yet for all their grandeur and majesty, massive stars are not eternal. Their lives are fleeting, marked by a tumultuous journey towards their ultimate demise. When a massive star exhausts its nuclear fuel, it embarks on a cataclysmic collapse, triggering a supernova, an explosive event that outshines entire galaxies and scatters heavy elements across the cosmos. In the aftermath of a supernova, the remnants of the star may give rise to some of the most enigmatic objects in the universe, from neutron stars, dense stellar corpses pulsating with intense energy, to black holes, cosmic singularities where the laws of physics break down and the very fabric of space-time is warped beyond recognition. The study of massive stars is not merely an academic pursuit, but a journey of discovery that unlocks the secrets of the universe itself. By peering into the depths of space and time, astronomers gain invaluable insights into the processes that govern the birth, life, and death of stars, shedding light on the fundamental forces that shape the cosmos and our place within it. In the vast expanse of the cosmos, where stars reign supreme as the celestial luminaries that illuminate the darkness of space, there exist titanic behemoths of unparalleled scale and power, supermassive stars whose brilliance outshines even the most radiant of their stellar brethren. These cosmic giants, born from the crucible of interstellar clouds, defy conventional understanding and challenge the limits of cosmic imagination with their extraordinary characteristics and immense significance in shaping the destiny of the universe. Exploring the characteristics of supermassive stars is to embark on a journey into the heart of cosmic extremes, where the forces of gravity and nuclear fusion converge to create some of the most awe-inspiring phenomena in the cosmos. Unlike their smaller counterparts, supermassive stars possess an incomprehensible mass, measured in magnitudes that dwarf even the most massive of ordinary stars. At the core of these stellar behemoths lies a cosmic inferno of unimaginable heat and pressure, where nuclear fusion reigns supreme and elements are forged in the fiery crucible of their cores. Unlike smaller stars, which burn through their nuclear fuel at a gradual pace, supermassive stars are cosmic powerhouses, consuming their hydrogen fuel reserves at an astonishing rate, driving their luminosity to levels that defy comprehension. The sheer size and power of supermassive stars make them cosmic heavyweights, casting their radiant glow across the cosmos and shaping the environments in which they reside. Their luminosity far surpasses that of ordinary stars, illuminating the heavens with a brilliance that outshines entire galaxies and dominates the cosmic landscape with their formidable presence. But it is not merely their size and luminosity that set supermassive stars apart. It is their unique characteristics and remarkable behavior that captivate the imagination of astronomers and stargazers alike. From their turbulent atmospheres to their violent deaths in cataclysmic supernova explosions, supermassive stars are cosmic phenomena of unparalleled significance and complexity. Throughout their lives, supermassive stars exhibit a dynamic interplay of forces, from the relentless pull of gravity that compresses their cores to the fiery inferno of nuclear fusion that sustains their brilliance. They shine with a luminosity that rivals the combined light of entire galaxies, shaping the cosmic landscape and influencing the evolution of the universe on a grand scale. Yet, for all their grandeur and majesty, supermassive stars are not eternal. Their lives are fleeting, marked by a tumultuous journey towards their ultimate demise. When a supermassive star exhausts its nuclear fuel, it embarks on a cataclysmic collapse, triggering a supernova, an explosive event that outshines entire galaxies and scatters heavy elements across the cosmos. In the aftermath of a supernova, the remnants of the star may give rise to some of the most enigmatic objects in the universe, from neutron stars, dense stellar corpses pulsating with intense energy, to black holes, cosmic singularities where the laws of physics break down and the very fabric of space-time is warped beyond recognition. The exploration of supermassive stars is not merely an academic pursuit, but a journey of discovery that unlocks the secrets of the universe itself. By peering into the depths of space and time, astronomers gain invaluable insights into the processes that govern the birth, life, and death of stars, shedding light on the fundamental forces that shape the cosmos and our place within it. Supermassive stars are a class of stellar objects characterized by their extraordinary mass, luminosity, and significance in the cosmos. These cosmic behemoths defy conventional understanding, pushing the boundaries of stellar physics and shaping the destiny of galaxies and the universe itself. Definition: supermassive stars are defined by their immense mass, which far exceeds that of ordinary stars. While there is no strict cutoff defining what constitutes a supermassive star, they typically have masses many times greater than that of our Sun, often ranging from tens to hundreds of times the solar mass. Their sheer size and gravitational influence set them apart as cosmic heavyweights, dominating the regions of space they inhabit and shaping the dynamics of their galactic environments. Supermassive stars can be classified based on various criteria, including their mass, luminosity, and evolutionary stage. One common classification scheme categorizes supermassive stars into three main groups. Low-mass supermassive stars. These are supermassive stars with masses on the lower end of the spectrum, typically ranging from tens to a few hundred times the mass of the Sun. While still formidable in size and luminosity compared to ordinary stars, they are relatively less massive than their higher mass counterparts. Low-mass supermassive stars may exhibit similar characteristics to high-mass stars, such as intense nuclear fusion reactions and stellar winds, but their evolutionary paths and eventual fates may differ. Intermediate mass supermassive stars. Intermediate mass supermassive stars occupy the middle ground between low mass and high mass supermassive stars, with masses ranging from a few hundred to several thousand times that of the Sun. These stars straddle the boundary between the two extremes, exhibiting a mix of characteristics from both groups. They may undergo unique evolutionary processes and exhibit distinctive features in their spectra and luminosity profiles. High-mass supermassive stars. High-mass supermassive stars represent the most massive and luminous members of the class, with masses ranging from several thousand to millions of times that of the Sun. These cosmic giants shine with an intense brilliance that outshines entire galaxies, casting their radiant glow across the cosmos and influencing the evolution of their galactic hosts. High-mass supermassive stars are often associated with regions of active star formation and are thought to play a crucial role in shaping the structure and dynamics of galaxies through their gravitational interactions and stellar feedback. Beyond these broad classifications, supermassive stars may also be categorized based on their evolutionary stage, spectral characteristics, and other observable properties. Regardless of their specific classification, supermassive stars stand as cosmic marvels that challenge our understanding of stellar physics and inspire wonder in the hearts and minds of astronomers and stargazers alike. Comparing supermassive stars to the Sun reveals profound differences in scale, luminosity, and significance in the cosmos, highlighting the extraordinary diversity of stellar phenomena and the vast range of cosmic possibilities. Mass. The most striking difference between supermassive stars and the Sun lies in their mass. Supermassive stars are characterized by their immense mass, which can range from tens to millions of times that of the Sun. In contrast, the Sun is a relatively modest star, with a mass of about 330,000 times that of Earth. This vast difference in mass is a defining feature of supermassive stars, setting them apart as cosmic heavyweights with gravitational influences that extend far beyond those of ordinary stars. Luminosity. Another key distinction between supermassive stars and the Sun is their luminosity, the amount of energy they emit as light and other forms of radiation. Supermassive stars shine with an intensity that far surpasses that of the Sun, casting their radiant glow across the cosmos and illuminating the darkness of space with their brilliant light. In contrast, the Sun's luminosity is relatively modest compared to that of supermassive stars, although it still outshines all other stars in the solar neighborhood. Size. Due to their immense mass and luminosity, supermassive stars are typically much larger in size than the Sun. While the Sun has a diameter of about 1.4 million kilometers, supermassive stars can span hundreds or even thousands of times the diameter of the Sun, stretching the limits of cosmic scale and defying conventional notions of stellar dimensions. Evolutionary stage. Supermassive stars and the Sun also differ in their evolutionary stages and life cycles. The Sun is currently in the middle of its main sequence phase, where it fuses hydrogen into helium in its core and shines steadily for billions of years. In contrast, supermassive stars evolve at a much faster pace, burning through their nuclear fuel reserves at an accelerated rate and undergoing rapid transformations that culminate in cataclysmic events such as supernova explosions. Galactic significance. Perhaps the most profound difference between supermassive stars and the Sun lies in their significance within the broader context of galaxies and the universe. Supermassive stars are often found in regions of active star formation and are thought to play a crucial role in shaping the structure and dynamics of galaxies through their gravitational interactions and stellar feedback. In contrast, the Sun is just one of billions of stars in the Milky Way galaxy, exerting a relatively minor influence on its galactic environment. The immense size of supermassive stars is the result of a complex interplay of various factors, including their formation processes, evolutionary pathways, and the physical properties of the environments in which they reside. Understanding the factors contributing to their massive size provides valuable insights into the dynamics of stellar formation and evolution, shedding light on the extraordinary phenomena that shape the cosmos. Accretion of mass. Supermassive stars are born from the gravitational collapse of massive molecular clouds, dense concentrations of gas and dust scattered throughout the galaxy. These molecular clouds serve as cosmic incubators, nurturing the seeds of future stars and providing the raw materials necessary for their formation. As gravity draws together particles of gas and dust within these clouds, they accumulate mass and density, eventually reaching a critical threshold where nuclear fusion ignites in their cores, marking the birth of a supermassive star. The accretion of mass plays a crucial role in determining the size of supermassive stars, as larger amounts of material lead to more massive stars. In regions of high-density gas and dust, such as the centers of galaxies or regions of active star formation, the accretion process can proceed at an accelerated rate, resulting in the formation of exceptionally massive stars. High initial mass. Another factor contributing to the massive size of supermassive stars is their high initial mass, a consequence of the conditions present during their formation. In regions where molecular clouds are particularly dense and massive, the seeds of future stars are born with a higher initial mass, setting the stage for the formation of supermassive stars. Additionally, the presence of companion stars or stellar clusters can also contribute to the high initial mass of supermassive stars through interactions such as mass transfer or mergers. These interactions can result in the accumulation of additional mass, further fueling the growth of already massive stars. Rapid nuclear fusion. Once nuclear fusion ignites in the cores of supermassive stars, the intense heat and pressure generated by this process drive the fusion of hydrogen into helium at a rapid pace. Unlike smaller stars like the Sun, which burn through their nuclear fuel at a relatively leisurely pace, supermassive stars consume their hydrogen fuel reserves at an accelerated rate, leading to rapid growth and expansion. The rapid pace of nuclear fusion in supermassive stars results in higher rates of energy production and greater outward pressure, pushing against the force of gravity and allowing these massive stars to maintain their colossal size. However, this rapid consumption of nuclear fuel also means that the lifespan of supermassive stars is relatively short compared to smaller stars, leading to rapid evolutionary changes and eventual cataclysmic events such as supernova explosions. Stellar feedback. As supermassive stars evolve, they release vast amounts of energy and radiation into their surroundings, exerting a significant influence on their galactic environments through processes known as stellar feedback. This feedback can take various forms, including stellar winds, radiation pressure, and supernova explosions, all of which can contribute to the dispersal of surrounding gas and dust and the regulation of star formation activity. In regions of active star formation or dense galactic nuclei, the presence of supermassive stars can enhance the efficiency of star formation by compressing nearby gas and triggering the collapse of molecular clouds. Conversely, the explosive deaths of supermassive stars and supernova explosions can inject heavy elements into the interstellar medium, enriching the galactic environment and influencing the formation of future generations of stars. The process of a supernova explosion is a cataclysmic event of cosmic proportions, marking the violent demise of a massive star at the end of its evolutionary journey. Driven by the relentless forces of gravity and nuclear fusion, a supernova explosion represents one of the most energetic phenomena in the universe, releasing an unfathomable amount of energy in a fraction of a second and illuminating the heavens with its brilliant light. Core collapse. The journey towards a supernova explosion begins when a massive star exhausts its nuclear fuel reserves, leading to a dramatic collapse of its core under the force of gravity. As nuclear fusion ceases, the outward pressure generated by the fusion reactions diminishes, allowing gravity to overcome and compress the star's core to extraordinary densities and temperatures. Rebound and shockwave formation. As the core collapses, it reaches densities and temperatures sufficient to trigger a rebound effect, sending a powerful shockwave rippling through the star's outer layers. This shockwave, fueled by the immense energy released during the core collapse, blasts outward with tremendous force, tearing through the star's interior and initiating the explosive phase of the supernova. Ejection of outer layers. The shockwave generated by the collapsing core rapidly accelerates as it races through the star's outer layers, causing them to be violently expelled into space at speeds approaching a significant fraction of the speed of light. This ejection of material results in the formation of a luminous shell of hot gas and dust known as a supernova remnant, which expands outward into the surrounding interstellar medium. Radiation and neutrino emission. In addition to the ejection of material, a supernova explosion also emits vast amounts of radiation across the electromagnetic spectrum, from gamma rays and X-rays to visible light and radio waves. This intense radiation illuminates the surrounding space and can be observed by astronomers across the entire electromagnetic spectrum. Furthermore, during the core collapse phase, copious amounts of neutrinos are produced as a byproduct of the nuclear reactions occurring within the collapsing core. These neutrinos stream outwards from the collapsing star, carrying away a significant portion of the gravitational energy released during the collapse and playing a crucial role in driving the supernova explosion. Formation of remnants. Following the supernova explosion, what remains of the star's core may give rise to some of the most exotic objects in the universe depending on the mass of the progenitor star. For stars with initial masses below a certain threshold, the core may collapse into a dense stellar remnant known as a neutron star, a city-sized object composed primarily of densely packed neutrons. For more massive stars, the core collapse may result in the formation of a black hole, an enigmatic singularity where gravity's grip is so intense that not even light can escape. The process of a supernova explosion is a dramatic and violent event that marks the end of one stellar life and the birth of new cosmic phenomena. From the cataclysmic collapse of a massive star's core to the luminous explosion that follows, a supernova explosion is a testament to the extraordinary forces that shape the universe and the profound interconnectedness of all things in the grand tapestry of the cosmos. The supernova phenomenon is one of the most spectacular and energetic events in the universe, marking the explosive end of a massive star's life. This cataclysmic event releases an immense amount of energy, outshining entire galaxies and briefly outshining all the other stars in its host galaxy combined. Understanding the supernova phenomenon requires delving into the intricate processes that drive this dramatic event, from the gravitational collapse of the star's core to the violent ejection of its outer layers. Core collapse. The journey towards a supernova explosion begins when a massive star, typically many times more massive than our Sun, exhausts its nuclear fuel. In the absence of the energy generated by nuclear fusion, the inward force of gravity overwhelms the outward pressure of radiation, causing the star's core to collapse under its own weight. Shockwave formation. As the core collapses, it reaches densities and temperatures where nuclear reactions occur explosively, generating a burst of energy that reverberates outward through the star's layers. This burst of energy creates a powerful shockwave that blasts through the star's outer layers, initiating the explosive phase of the supernova. Ejection of outer layers. The shockwave generated by the collapsing core rapidly accelerates as it races through the star's outer layers, causing them to be violently expelled into space. This ejection of material results in the formation of a luminous shell of hot gas and dust, known as a supernova remnant, which expands outward into the surrounding interstellar medium. Types of supernova. Supernovae are classified into different types based on the mechanisms that drive their explosions. Type Ia supernovae are thought to occur in binary star systems, where one star is a white dwarf and the other is a companion star. When the white dwarf accretes enough mass from its companion, it undergoes a runaway nuclear fusion reaction, leading to a thermonuclear explosion. Type II supernovae, on the other hand, occur when massive stars reach the end of their lives and undergo core collapse. These are the most common type of supernova and are responsible for enriching the interstellar medium with heavy elements forged in the star's core. Supernova remnants. Following the supernova explosion, what remains of the star's core may give rise to some of the most exotic objects in the universe. For stars with initial masses below a certain threshold, the core may collapse into a dense stellar remnant known as a neutron star, a city-sized object composed primarily of densely packed neutrons. For more massive stars, the core collapse may result in the formation of a black hole, an enigmatic singularity where gravity's grip is so intense that not even light can escape. Surrounding these remnants is the expanding shell of material ejected during the supernova explosion, known as a supernova remnant, which continues to expand and dissipate into the interstellar medium over time. The supernova phenomenon is a testament to the extraordinary forces that shape the cosmos, from the gravitational collapse of massive stars to the explosive release of energy that illuminates the heavens and enriches the universe with heavy elements. By studying supernovae, astronomers gain valuable insights into the life cycles of stars, the formation of stellar remnants, and the evolution of galaxies and the universe as a whole. The end of a supermassive star's life cycle is a culmination of processes that reflect the extreme conditions and forces at play within these cosmic giants. While the specifics may vary depending on factors such as mass, metallicity, and rotation rate, several key mechanisms contribute to the demise of supermassive stars and their transformation into exotic stellar remnants or black holes. Depletion of nuclear fuel. Like all stars, supermassive stars rely on nuclear fusion to sustain their luminosity and counteract the inward pull of gravity. However, due to their tremendous mass, supermassive stars burn through their nuclear fuel at an accelerated rate, leading to a relatively short lifespan compared to lower-mass stars. The fusion of hydrogen into heavier elements in the star's core is the primary energy source, but eventually, the star exhausts its nuclear fuel, leading to the cessation of fusion reactions. Core collapse. With the cessation of nuclear fusion, the core of the supermassive star loses its ability to generate outward pressure, allowing gravity to take over. The core begins to collapse under its own weight, rapidly increasing in temperature and density. This collapse proceeds until the core reaches conditions where further collapse is halted by electron degeneracy pressure, or, for more massive stars, neutron degeneracy pressure. Formation of exotic remnants. The fate of the supermassive star's core depends on its mass. For cores below a certain threshold, about 2-3 solar masses, electron degeneracy pressure halts further collapse, resulting in the formation of a dense stellar remnant known as a neutron star. Neutron stars are incredibly dense objects composed primarily of neutrons, packing the mass of several suns into a sphere just a few kilometers in diameter. However, if the core's mass exceeds the neutron degeneracy pressure limit, around 2-3 solar masses, even this force cannot prevent further collapse. In such cases, the core collapses indefinitely, forming a singularity, a point of infinite density and zero volume, known as a black hole. Black holes exert an intense gravitational pull from which not even light can escape, rendering them invisible to direct observation. Supernova explosions. In some cases, the collapse of a supermassive star's core triggers a cataclysmic explosion known as a supernova. These explosions release an immense amount of energy, briefly outshining entire galaxies and dispersing heavy elements forged within the star's core into the surrounding interstellar medium. Supernovae play a crucial role in enriching the cosmos with elements essential for the formation of planets, stars, and life itself. Stellar feedback and galactic evolution. The demise of supermassive stars through supernova explosions or the formation of black holes also has profound implications for the evolution of galaxies. These events inject energy and heavy elements into the interstellar medium, influencing star formation rates, galaxy dynamics, and the chemical composition of future generations of stars. Supermassive stars thus play a crucial role in shaping the structure and evolution of galaxies over cosmic timescales. Supernovae are among the most explosive events in the universe, releasing staggering amounts of energy in a brief, dazzling display of cosmic fury. These cataclysmic explosions mark the violent end of a massive star's life and play a crucial role in shaping the evolution of galaxies and the cosmos as a whole. An overview of the explosive nature of supernovae reveals the extraordinary forces and phenomena involved in these cosmic fireworks. Energy release. Supernovae unleash an immense amount of energy, often equivalent to the energy output of an entire galaxy over millions of years, in just a matter of seconds to weeks. This energy release results from the sudden collapse of a massive star's core and the subsequent rebound and explosion of its outer layers. The energy released during a supernova explosion can briefly outshine entire galaxies and is detectable across the entire electromagnetic spectrum, from gamma rays to radio waves. Shockwave propagation. The core collapse of a massive star initiates a powerful shockwave that propagates outward through the star's layers, compressing and heating the surrounding material to extreme temperatures and densities. This shockwave accelerates as it travels through the star's outer layers, eventually blasting them away into space at speeds of thousands of kilometers per second. The shockwave also triggers nuclear fusion reactions in the star's outer layers, producing vast amounts of light and heat. Ejection of material. One of the defining features of supernovae is the ejection of material from the exploding star into the surrounding interstellar medium. This ejected material, consisting of heavy elements synthesized within the star's core during its lifetime, enriches the interstellar medium with elements essential for the formation of new stars, planets, and even life itself. The expanding shell of ejected material forms a supernova remnant, which can persist for thousands to millions of years and serve as a laboratory for studying the processes of stellar evolution and nucleosynthesis. Types of supernovae. Supernovae are classified into different types based on the mechanisms that drive their explosions. Type Ia supernovae occur in binary star systems, where one star is a white dwarf and the other is a companion star. When the white dwarf accretes enough mass from its companion, it undergoes a runaway nuclear fusion reaction, leading to a thermonuclear explosion. Type II supernovae, on the other hand, occur when massive stars reach the end of their lives and undergo core collapse. These are the most common type of supernova and are responsible for enriching the interstellar medium with heavy elements forged in the star's core. Cosmic significance. Supernovae play a crucial role in the evolution of galaxies and the cosmos as a whole. They inject energy and heavy elements into the interstellar medium, influencing star formation rates, galaxy dynamics, and the chemical composition of future generations of stars. Supernovae are also thought to be responsible for the production of most of the elements heavier than iron, which are essential for the formation of planets, stars, and life as we know it. The explosive nature of supernovae carries profound implications and consequences that reverberate throughout the cosmos, influencing the evolution of galaxies, the formation of celestial bodies, and even the existence of life itself. Understanding these implications sheds light on the interconnectedness of cosmic phenomena and the dynamic nature of the universe. Galactic evolution. Supernovae play a crucial role in the evolution of galaxies, shaping their structure, dynamics, and chemical composition over cosmic timescales. The energy and heavy elements released during supernova explosions enrich the interstellar medium, providing the raw materials necessary for the formation of new stars, planets, and even life. Supernova also inject energy into the interstellar medium, triggering shock waves that compress gas and initiate the collapse of molecular clouds, leading to the formation of new stars and stellar systems. Stellar populations. The frequency and distribution of supernova explosions influence the populations of stars within galaxies, affecting their age distribution, metallicity, and luminosity. Supernovae contribute to the dispersal of heavy elements synthesized in the cores of massive stars, enriching the interstellar medium and influencing the chemical composition of subsequent generations of stars. The presence of supernova remnants serves as a record of past stellar activity and provides insights into the history of star formation within galaxies. Formation of celestial bodies. Supernovae are responsible for the production of many of the elements heavier than iron, which are essential for the formation of planets, stars, and life as we know it. The explosive ejection of material from supernova explosions enriches the interstellar medium with these heavy elements, providing the building blocks for the formation of rocky planets, metal-rich stars, and even organic molecules necessary for the emergence of life. Without supernova, the universe would lack the diversity of elements necessary for the formation of complex celestial bodies and the emergence of life-sustaining environments. Cosmic feedback. Supernovae also play a crucial role in regulating star formation activity within galaxies through processes known as stellar feedback. The energy and radiation released during supernova explosions can heat and disperse surrounding gas clouds, suppressing the formation of new stars in regions of high supernova activity. Conversely, supernova shockwaves can compress nearby gas clouds, triggering the collapse and formation of new stars in regions of low star formation activity. This feedback loop helps maintain the balance between stellar birth and death within galaxies, shaping their evolution and morphology over time. Cosmological significance. Supernovae serve as important cosmological probes for measuring cosmic distances and studying the expansion rate of the universe. Type Ia supernovae, in particular, are used as standard candles to determine the distances to distant galaxies and constrain the parameters of cosmological models. The discovery of the accelerated expansion of the universe, attributed to dark energy, was made possible by observations of distant supernovae, highlighting their significance in our understanding of the cosmos on the largest scales. The impact of supermassive star explosions on the universe is profound, shaping the dynamics, composition, and evolution of galaxies and the cosmos as a whole. These cataclysmic events release immense amounts of energy and heavy elements into the interstellar medium, influencing star formation, galactic structure, and even the conditions necessary for the emergence of life. Exploring the impact of supermassive star explosions provides valuable insights into the interconnectedness of cosmic phenomena and the dynamic nature of the universe. Galactic dynamics. Supermassive star explosions, such as supernovae and hypernovae, inject energy and momentum into the interstellar medium, triggering shockwaves that propagate through galaxies and influence their dynamics. These shockwaves compress and heat surrounding gas clouds, triggering the collapse and formation of new stars in regions of low star formation activity. The energy released during supermassive star explosions can also drive galactic outflows, expelling gas and dust from galaxies and regulating their star formation rates over cosmic timescales. Chemical enrichment. One of the most significant impacts of supermassive star explosions is the production and dissemination of heavy elements synthesized in the cores of massive stars. These elements, including carbon, oxygen, nitrogen, and iron, are essential building blocks for the formation of planets, stars, and life itself. The explosive ejection of material from supermassive star explosions enriches the interstellar medium with these heavy elements, influencing the chemical composition of subsequent generations of stars and the environments in which they form. Stellar populations. Supermassive star explosions influence the populations of stars within galaxies, affecting their age distribution, metallicity, and luminosity. The presence of supernova remnants serves as a record of past stellar activity and provides insights into the history of star formation within galaxies. Supermassive star explosions also contribute to the dispersal of heavy elements synthesized in the cores of massive stars, enriching the interstellar medium and influencing the chemical composition of subsequent generations of stars. Cosmic feedback. Supermassive star explosions play a crucial role in regulating star formation activity within galaxies through processes known as stellar feedback. The energy and radiation released during these explosions can heat and disperse surrounding gas clouds, suppressing the formation of new stars in regions of high supermassive star activity. Conversely, supermassive star explosions can compress nearby gas clouds, triggering the collapse and formation of new stars in regions of low star formation activity. This feedback loop helps maintain the balance between stellar birth and death within galaxies, shaping their evolution and morphology over time. Cosmological significance. Supermassive star explosions serve as important cosmological probes for studying the evolution and expansion of the universe. Type Ia supernovae in particular are used as standard candles to determine the distances to distant galaxies and constrain the parameters of cosmological models. The discovery of the accelerated expansion of the universe, attributed to dark energy, was made possible by observations of distant supermassive star explosions, highlighting their significance in our understanding of the cosmos on the largest scales. Supernova explosions play a crucial role in the formation and dissemination of elements throughout the universe, enriching the interstellar medium with a diverse array of chemical elements essential for the formation of planets, stars, and life itself. Understanding the process by which supernovae forge and distribute elements provides valuable insights into the chemical evolution of galaxies and the origins of the elements that make up the cosmos. Nucleosynthesis in stellar cores. The formation of elements in supernova explosions begins within the cores of massive stars, where nuclear fusion reactions convert lighter elements into heavier ones through a process known as nucleosynthesis. During the course of their lives, massive stars fuse hydrogen into helium, helium into heavier elements like carbon and oxygen, and continue to fuse elements in progressively heavier shells until they reach iron in their cores. Core collapse and explosive nucleosynthesis. When a massive star exhausts its nuclear fuel and undergoes core collapse, the sudden increase in temperature and pressure triggers a rapid series of nuclear reactions, known as explosive nucleosynthesis, within its collapsing core. These reactions synthesize elements heavier than iron, such as nickel, copper, zinc, and even elements as heavy as uranium and plutonium in a matter of seconds to minutes. Neutron capture processes. Explosive nucleosynthesis in supernova explosions is facilitated by rapid neutron capture processes, including the R process, rapid neutron capture, and S process, slow neutron capture. In the R process, neutrons are rapidly captured by existing nuclei, leading to the formation of neutron-rich isotopes of heavy elements. The S process, on the other hand, occurs in the outer layers of massive stars during their normal evolution and involves the slow capture of neutrons over long timescales. Ejection of material. The explosive ejection of material from supernova explosions disperses these newly synthesized elements into the surrounding interstellar medium, enriching it with heavy elements forged within the star's core. The expanding shell of ejected material forms a supernova remnant, which can persist for thousands to millions of years and serve as a reservoir of heavy elements for future generations of stars and planets. Chemical enrichment of galaxies. The enrichment of the interstellar medium with heavy elements synthesized in supernova explosions has profound implications for the chemical evolution of galaxies. These elements serve as the building blocks for the formation of new stars, planets, and even life. The presence of heavy elements influences the characteristics of subsequent generations of stars, affecting their metallicity, luminosity, and evolutionary pathways. Over cosmic timescales, the chemical composition of galaxies evolves as a result of ongoing stellar birth, death, and recycling of material through processes such as supernova explosions. Supernova explosions have significant potential effects on nearby celestial bodies, influencing their environments, compositions, and even their fates. These effects can vary depending on factors such as the distance from the supernova, the mass and composition of the nearby objects, and the intensity of the explosion. Considering these potential effects provides insights into the complex interplay between supernova and their surrounding cosmic environments. Radiation and shockwaves. One of the most immediate effects of a nearby supernova explosion is the release of intense radiation and shockwaves that propagate through the interstellar medium. These shockwaves compress and heat surrounding gas clouds, triggering the collapse and formation of new stars in regions of low star formation activity. The intense radiation from the explosion can also ionize nearby gas clouds, altering their chemical composition and influencing the formation of molecules and dust grains. Ejection of material. The explosive ejection of material from a supernova explosion can have profound effects on nearby celestial bodies, including planets, moons, and asteroids. The impact of supernova ejecta on these objects can range from the deposition of heavy elements and isotopes to the disruption or destruction of their surfaces. For example, the deposition of radioactive isotopes, such as iron-60 from supernova ejecta, has been detected in deep-sea sediments on Earth, providing evidence of nearby supernova explosions in the distant past. Ionization and heating. Supernova explosions can ionize and heat the surrounding interstellar medium, creating expanding bubbles of ionized gas known as H2 regions. These regions can have significant effects on nearby celestial bodies, including the ionization and heating of their atmospheres, the acceleration of charged particles, and the disruption of magnetic fields. In extreme cases, the intense radiation and heating from supernova explosions can strip away the atmospheres of nearby planets or disrupt the orbits of comets and asteroids. Chemical enrichment. One of the long-term effects of supernova explosions is the chemical enrichment of nearby celestial bodies with heavy elements synthesized in the explosion. These elements can be incorporated into the surfaces of planets, moons, and asteroids, altering their compositions and providing valuable clues about the history of nearby supernova activity. The presence of supernova-derived isotopes in meteorites and lunar samples suggests that such events have influenced the chemical evolution of the solar system. Stellar feedback. Supernova explosions can also have indirect effects on nearby celestial bodies through processes known as stellar feedback. The energy and radiation released during supernova explosions can drive galactic outflows, expelling gas and dust from galaxies and regulating their star formation rates over cosmic timescales. These outflows can influence the formation and evolution of nearby stars, planets, and other celestial bodies by altering the chemical composition and density of the surrounding interstellar medium. Current research on supernovae and their effects on the universe spans a wide range of topics, from observational studies of supernova explosions and their remnants to theoretical modeling of the processes that drive these cataclysmic events. Future prospects in this field hold the promise of further unraveling the mysteries of supernova and their role in shaping the cosmos, as well as advancing our understanding of fundamental astrophysical phenomena. Observational studies. Current research efforts focus on observing supernova explosions across the electromagnetic spectrum, from gamma rays to radio waves, to gain insights into their properties, progenitor stars, and environments. Advanced telescopes and observatories such as the Hubble Space Telescope, the Chandra X-ray Observatory, and the Atacama Large Millimeter Submillimeter Array, ALMA, enable astronomers to study supernovae in unprecedented detail and resolution. Future prospects in observational studies include the development of next-generation telescopes and detectors with enhanced sensitivity and capabilities for observing supernovae at various stages of their evolution. These advancements will enable astronomers to detect and study increasingly distant and faint supernovae, shedding light on the early universe and the processes that govern the formation and evolution of galaxies. Theoretical modeling. Theoretical modeling plays a crucial role in understanding the physical processes that drive supernova explosions, including core collapse, shockwave propagation, and nucleosynthesis. Current research efforts focus on refining and improving existing theoretical models of supernova explosions through high-performance computing simulations and numerical experiments. Future prospects in theoretical modeling include the development of more sophisticated and realistic models that incorporate a broader range of physical processes and conditions, such as neutrino transport, magnetohydrodynamics, and nuclear reaction networks. These advanced models will provide valuable insights into the mechanisms that govern supernova explosions and help astronomers interpret observational data more accurately. Multi-messenger astronomy. Recent advancements in multi-messenger astronomy, which combines observations from different types of cosmic messengers such as electromagnetic radiation, gravitational waves, and neutrinos, have opened up new avenues for studying supernovae and their effects on the universe. Current research efforts focus on detecting and characterizing supernova explosions using multiple messengers to gain complementary insights into their properties and dynamics. Future prospects in multi-messenger astronomy include the continued development of observational facilities and techniques for detecting gravitational waves and neutrinos from supernova explosions. These advancements will enable astronomers to study supernovae in unprecedented detail and precision, providing new constraints on their progenitor stars, explosion mechanisms, and evolutionary pathways. Cosmological implications. Supernovae have profound cosmological implications, serving as important cosmological probes for studying the expansion rate of the universe and constraining the parameters of cosmological models. Current research efforts focus on using observations of distant supernovae to measure cosmic distances and test theoretical predictions of cosmic expansion and dark energy. Future prospects in cosmological studies include the development of larger and more comprehensive surveys of supernovae and other cosmological probes, such as baryon acoustic oscillations and the cosmic microwave background radiation. These surveys will provide increasingly precise measurements of cosmological parameters and help address key questions about the nature of dark energy, dark matter, and the ultimate fate of the universe. Recent discoveries related to supermassive stars have shed new light on these cosmic behemoths and expanded our understanding of their properties, formation mechanisms, and evolutionary pathways. These discoveries have been made possible by advances in observational techniques, theoretical modeling, and computational simulations, allowing astronomers to probe the depths of space with unprecedented precision and resolution. An overview of some of the most significant recent discoveries related to supermassive stars highlights the dynamic nature of this field and its implications for our understanding of the universe. Identification of supermassive star candidates. Recent observational surveys have identified several candidate supermassive stars, objects with masses significantly exceeding those of typical massive stars in various regions of the Milky Way and other galaxies. These candidates exhibit extreme luminosities and temperatures, suggesting that they may represent a distinct population of exceptionally massive and luminous stars.
Studying these supermassive star candidates provides insights into the upper limits of stellar mass and the conditions under which such massive stars form and evolve. Probing the formation environment. Observational studies of star-forming regions have revealed the presence of dense molecular clouds and massive stellar clusters where supermassive stars are believed to form. These studies have provided valuable insights into the physical conditions and processes that govern the formation of supermassive stars, including the role of gravitational collapse, turbulent fragmentation, and accretion of surrounding material. By tracing the evolutionary history of these star-forming regions, astronomers can reconstruct the formation pathways of supermassive stars and elucidate the factors that influence their properties. Understanding mass loss and evolution. Recent theoretical studies and numerical simulations have elucidated the mechanisms by which supermassive stars lose mass and evolve over time. These studies have revealed that supermassive stars undergo intense mass loss through stellar winds, radiative-driven outflows, and eruptive events, which can significantly impact their evolution and ultimate fate. Understanding the mass loss processes in supermassive stars is crucial for predicting their observable properties, such as luminosity, temperature, and chemical composition, and for constraining theoretical models of stellar evolution. Role in cosmic feedback. Supermassive stars play a crucial role in cosmic feedback processes, influencing the formation and evolution of galaxies and the interstellar medium through their energetic radiation, stellar winds, and supernova explosions. Recent observational and theoretical studies have highlighted the importance of supermassive stars as sources of ionizing radiation, cosmic rays, and heavy elements, which can regulate star formation rates, drive galactic outflows, and enrich the interstellar medium with metals. Understanding the impact of supermassive stars on their cosmic environment is essential for unraveling the complex interplay between stellar feedback processes and galaxy evolution. Implications for black hole formation. Recent discoveries related to supermassive stars have implications for our understanding of the formation mechanisms of black holes, the ultimate fate of the most massive stars. Supermassive stars are thought to be progenitors of black holes with masses exceeding 100 solar masses, which can form through direct collapse or via the intermediate step of a pair instability supernova. Recent theoretical studies and numerical simulations have provided insights into the conditions under which supermassive stars collapse into black holes and the observational signatures of this process.
Ongoing studies and research initiatives related to supermassive stars encompass a wide range of topics, from observational surveys and theoretical modeling to computational simulations and interdisciplinary collaborations. These initiatives aim to address key questions about the formation, evolution, and impact of supermassive stars on the universe, as well as to advance our understanding of fundamental astrophysical processes. A discussion of some of the ongoing studies and research initiatives in this field highlights the dynamic nature of this area of astrophysics and its implications for our understanding of the cosmos. Observational surveys. Ongoing observational surveys are systematically searching for supermassive stars in various regions of the Milky Way and other galaxies, using advanced telescopes and instruments across the electromagnetic spectrum. These surveys aim to identify and characterize supermassive stars based on their distinctive observational signatures, such as extreme luminosities, temperatures, and spectral features. By compiling comprehensive catalogs of supermassive stars and their properties, astronomers can constrain theoretical models of stellar formation and evolution and investigate their roles in galactic dynamics and cosmic feedback processes. Multi-messenger astronomy. Recent advancements in multi-messenger astronomy, which combines observations from different types of cosmic messengers, such as electromagnetic radiation, gravitational waves, and neutrinos, have opened up new avenues for studying supermassive stars and their effects on the universe. Ongoing research initiatives focus on detecting and characterizing supermassive stars using multiple messengers to gain complementary insights into their properties, progenitors, and evolutionary pathways. By combining data from different observational techniques, astronomers can construct more comprehensive models of supermassive stars and their cosmic environments. Theoretical modeling and simulations. Ongoing theoretical modeling and computational simulations are exploring the physical processes that govern the formation, evolution, and fate of supermassive stars, including core collapse, mass loss, and nucleosynthesis. These studies aim to refine and improve existing theoretical models of supermassive stars through high-performance computing simulations and numerical experiments. By incorporating a broader range of physical processes and conditions such as neutrino transport, magnetohydrodynamics, and nuclear reaction networks, theoretical models can provide valuable insights into the mechanisms that drive supermassive star explosions and their observational manifestations. Interdisciplinary collaborations. Interdisciplinary collaborations between astronomers, astrophysicists, and researchers from other fields are fostering innovative approaches to studying supermassive stars and their impact on the universe. Ongoing collaborations include partnerships with computational scientists, data scientists, and machine learning experts to develop new algorithms and techniques for analyzing large datasets and extracting valuable insights from observational and theoretical data. By leveraging the expertise and resources of diverse research communities, interdisciplinary collaborations can accelerate progress in understanding supermassive stars and their role in shaping the cosmos. Education and outreach. Ongoing efforts in education and outreach are raising public awareness about supermassive stars and engaging students and enthusiasts in scientific inquiry and discovery. Educational programs, public lectures, and citizen science projects provide opportunities for people of all ages and backgrounds to learn about supermassive stars and contribute to ongoing research initiatives. By fostering a sense of curiosity and wonder about the universe, education and outreach efforts inspire the next generation of astronomers and scientists to explore the mysteries of supermassive stars and the cosmos. Speculating on the future of understanding and observing supermassive star explosions involves considering the potential advancements in observational techniques, theoretical modeling, and interdisciplinary collaborations that may shape the field in the coming years. While it's challenging to predict specific breakthroughs, several trends and developments suggest exciting possibilities for unraveling the mysteries of these cosmic phenomena and their implications for our understanding of the universe. Advancements in observational techniques. Future advancements in observational techniques, including next-generation telescopes and detectors across multiple wavelengths, will enable astronomers to study supermassive star explosions with unprecedented sensitivity, resolution, and coverage. Space-based observatories, such as the James Webb Space Telescope (JWST), and ground-based facilities like the Extremely Large Telescope (ELT), will provide new capabilities for observing supermassive star explosions in various environments and at different evolutionary stages. These advancements will allow astronomers to detect and characterize a broader range of supermassive star explosions, including those occurring in distant galaxies and at earlier cosmic epochs. Multi-messenger astronomy, the emerging field of multi-messenger astronomy, which combines observations from different types of cosmic messengers, such as electromagnetic radiation, gravitational waves, and neutrinos, holds great promise for studying supermassive star explosions and their effects on the universe. Future observatories and detector networks, such as the Laser Interferometer Space Antenna, LISA, for gravitational waves and next-generation neutrino observatories, will enable astronomers to detect supermassive star explosions using multiple messengers simultaneously, providing complementary insights into their properties, progenitors, and evolutionary pathways. By combining data from different observational techniques, astronomers can construct more comprehensive models of supermassive star explosions and their cosmic environments. High-performance computing and data analysis. Advancements in high-performance computing and data analysis techniques will facilitate the modeling and simulation of supermassive star explosions with greater realism and accuracy. Future computational simulations will incorporate a broader range of physical processes and conditions, such as neutrino transport, magnetohydrodynamics, and nuclear reaction networks, allowing astronomers to explore the complex interactions and dynamics of supermassive star explosions in unprecedented detail. Machine learning algorithms and artificial intelligence techniques will also play an increasingly important role in analyzing large datasets and extracting valuable insights from observational and theoretical data, accelerating progress in understanding supermassive star explosions and their implications for the universe. Interdisciplinary collaborations and citizen science. Interdisciplinary collaborations between astronomers, astrophysicists, computational scientists, and researchers from other fields will foster innovative approaches to studying supermassive star explosions and their impact on the universe. Future collaborations may involve partnerships with experts in materials science, plasma physics, and nuclear astrophysics to develop new models and simulations of supermassive star explosions and their observable signatures. Citizen science projects and public engagement initiatives will also continue to play a crucial role in involving the broader community in scientific inquiry and discovery, providing opportunities for people of all ages and backgrounds to contribute to ongoing research efforts and make meaningful contributions to our understanding of supermassive star explosions and the cosmos. Supermassive star explosions represent some of the most energetic and cataclysmic events in the universe, releasing immense amounts of energy and heavy elements into the cosmos. These explosions play a crucial role in the chemical enrichment of galaxies, the formation of celestial bodies, and the regulation of star formation activity. By synthesizing and dispersing heavy elements throughout the interstellar medium, supermassive star explosions shape the evolution of galaxies, influence the properties of subsequent generations of stars and planets, and provide valuable insights into the history and dynamics of the universe. The study of supermassive star explosions has profound implications for astrophysics and cosmology, advancing our understanding of stellar evolution, galactic dynamics, and the nature of the universe. By combining observations, theoretical modeling, and interdisciplinary collaborations, astronomers are unraveling the mysteries of these cosmic phenomena and their role in shaping the cosmos. From the formation of elements in stellar cores to the enrichment of galaxies with heavy elements, supermassive star explosions provide a window into the fundamental processes that govern the universe on the largest scales.